presentation itself. At this time, I would like to introduce Pat Evans from CDM, and he will be speaking on ESTCP Project ER-2005-41. That was on perchlorate destruction and potable water production using membrane biofilm reduction and membrane filtration. Pat, I'll turn it over to you.
Thank you very much, Andrea. And so we'll go to the next slide here and want to introduce the team. And the slide is not advancing. There it goes. Okay, so want to introduce the team. In addition to myself, Pat Evans, the PI on this project, I have on the call Bruce Rittman, who is the co-PI. He's with Arizona State University, so he'll be presenting part of the project. Also have David Fries with APT Water, is the company who developed and constructed the technology, and then Jen Smith as well. In addition to these three organizations, want to acknowledge West Valley Water District, where the project was conducted. Then also there was an earlier phase of the project conducted at East Valley Water District. And then the California Department of Public Health, which was instrumental in reviewing the work plan and providing a letter of conditional acceptance for the technology. And then finally, the Water Research Foundation, which provided co-funding for the project and was instrumental in a survey that I'll be talking about. So going to the next slide, the membrane biofilm reactor, or the MBFR, is a technology where we use hollow fiber membranes to efficiently deliver hydrogen gas to a biofilm of autotrophic bacteria that reside on the outside of the membrane. And so, this hydrogen serves as an electron donor for biological reduction of contaminants such as nitrate and perchlorate. So this technology is distinct from ultrafiltration, where we're applying a vacuum on the inside of the membrane and drawing water through it. Here we're merely using the membranes to support the biofilm and to deliver hydrogen gas. Now, these hollow fibers must be placed into a reactor module in order to be able to scale up. And so APD Water has come up with a creative and innovative way to scale this up. And this involves placing these hollow fibers and weaving them into a fabric. And so the individual fibers are made out of polypropylene, and then they are woven into this fabric. This fabric can then be spirally wound around a central core tube, which delivers water to the spirally wound fibers, or the fabric. And so then this water goes in a spiral fashion, passing by all of these hydrogen-filled fibers, and then comes out and exits through the module. We also deliver hydrogen to the individual fibers. Each module ends up looking like this, and then we can place multiple modules into a reactor tank through which we recirculate the water. So the objectives of the project, there were three primary objectives. First was to demonstrate the cost and the performance of this MBFR. Second, the part that was led by Arizona State University was to conduct in-depth laboratory studies and mathematical modeling to better understand what the technology limitations were and how to overcome those limitations. And then finally, in the part that was co-funded by the Water Research Foundation, was to conduct a nationwide survey on biological drinking water treatment in an effort to increase the technology acceptance and use in the United States. The specific technology performance objectives for this project included contaminant destruction, where we were looking to remove perchlorate to less than 6 parts per billion. We also were looking at nitrate. Now the MCL for nitrate is 10 parts per million as nitrogen. However, the water that we used in this demonstration contained less than 10, so we had a more stringent performance objective of 0.5 milligrams per liter. We were also looking at the sum of nitrate and nitrite because we wanted to make sure we weren't just reducing nitrate to nitrite. Since the focus of the project was not just destruction of contaminants, but was also production of drinking water, we looked at a number of different criteria or objectives that were associated with production of drinking water. These are under the Safe Drinking Water Act, including disinfection, filtration, aesthetics, biological stabilization, which refers to when the water goes into the distribution system, does it remain stable or does it end up consuming up the disinfectant residual? And then reliability of the process. Going on to the next slide, performance objectives. There was also a number of qualitative performance objectives looking at safety, permit compliance, regulatory acceptance, and then robustness of the process. So now going on to slide number 8. The site was the West Valley Water District well number 22, and this was located here in Rialto. And there was the Superfund site here, which had 2 primary plumes. This is the Goodrich Superfund site. And so we had, this was a former agricultural well, had about 150 parts per billion of perchlorate, and then about 9 parts per million of nitrate nitrogen. And then we also had some VOCs, specifically TCE was present in this water. So going on to the next slide, number 10 here. This is the process flow diagram. And so what we have are a number of different elements. There's the gas supply, which included hydrogen as the electron donor, also air or nitrogen for sparging the membranes and doing biofilm control. We also had carbon dioxide that served 2 purposes. One was a source of carbon for the bacteria, and 2 was for pH control. Then we had the water supply coming from the well going into an equalization tank, and then we supplied phosphate nutrients to the bacteria as well. There were the 2 stages of the MBFR, each containing 7 of these MBFR modules, and these were operated in series. Following the MBFR treatment, we had a number of different processes to meet the Safe Drinking Water Act requirements, specifically aeration to remove residual dissolved organic carbon and to stabilize the water and remove any odors, media filtration to remove turbidity, and then disinfection with hypochlorite, and then the product tank where we took our final samples. Now this water following treatment was discharged back into a groundwater well, and so for that we ended up getting a permit from the Regional Water Quality Control Board of California, and they required that we do ion exchange and granular activated carbon treatment at the discharge. But these processes are not part of the main process that was being demonstrated. They were just for permit compliance. So going on to slide 11, here's some photos from the system. We can see here in the upper right are the whole system in the trailer at the lower right. We have our 2 tanks, our 2 stages, which we would switch back and forth and lead and lag. And then we have our aeration tank, followed by our filter, and then our post-water product tank, and then our equalization tank up here. In the top middle, we have our gas supply, and then on the left, we have a close-up photo of one of the modules, the core tube coming up, and then the small swage lock fitting is where the hydrogen would be injected. And then down in the bottom left, we have our 7 modules contained in a tank. Okay. So on the next slide, 12, the test design included 4 different phases. There was startup, where we constructed and initiated operation of the system with the objective of getting to that 6 parts per billion perchlorate and 0.5 milligrams per liter nitrate. And then optimization, where we varied a number of things to optimize the system. Followed that with steady state and challenge, which is the bulk of what I'll be presenting to you today. The steady state, we are looking at performance of the system with respect to our different performance objectives. And then challenge, looking at what would happen when we would have simulated upsets of the process. Going on to slide 13. Number of analyses were conducted associated with this project, looking at contaminant destruction, disinfection, biological stability, aesthetics, water chemistry, filtration, then also biofilm characteristics. And the biofilm characteristics were mainly looked at by Bruce Rittman at Arizona State University. One of the very interesting aspects of this that linked the field work with the laboratory work was the design and use of these side reactors. These were designed by APT Water. There were on each stage, we had 5 of these side reactors, and so for 2 stages, a total of 10 side reactors. This is a close-up of each one. It was using the same woven hollow fiber fabric that was used in the full-scale system. And then we would have the inlet on the left-hand side here for the hydrogen. And then we would have in the middle, on the bottom and the top, we'd have the inlet and outlet of our water. So we could go ahead and operate this over the duration of the experiment or the demonstration as we were seeing possible changes in water quality and just as the growth and the maturity of the biofilm would evolve. And then we could harvest these side reactors, send them to Arizona State University, and do a number of different analyses on these. So this gave us a lot of insight in terms of what was going on. So on the next slide, performance assessment, and on to slide 16. So here are some of the results from our steady state. Here we're looking at perchlorate removal, where we have perchlorate on the left-hand axis, and the red squares is the influent perchlorate. We're at about 120 or so about 150 micrograms per liter of perchlorate. And then we see in the first stage, after the first stage, we're reducing it down to about 60 or so micrograms per liter, so about a 50% reduction. And then finally in the second stage, we get down to about 9 micrograms per liter. The performance objective was less than 6 micrograms per liter, so we didn't meet this. We almost met it, but not quite. But we did get 94.4% removal, and this removal is quite consistent. And this was done at a flow rate of about 6 gallons per minute. So on the next slide, this is looking at the nitrate removal. In this case, the performance objective was 0.5 milligrams per liter, and we were able to get to 0.12 milligrams per liter, which is quite unusual for a lot of nitrate removal technologies, so it worked very well in that aspect. We were able to remove from about 10 down to about 2 milligrams per liter of nitrogen in the first stage, and then down to about 0.1 in the second stage. And so this was successful for a total of about 98.3% removal. Looking at Safe Drinking Water Act requirements, specifically looking at turbidity here during the steady state period, the goal was an NTU of 0.2, and we can see initially we were seeing some exceedances. The regulatory goal for turbidity is no greater than 1 all of the time and no greater than 0.3 95% of the time. We did see some exceedances here. This was due to a lack of optimization of the filter, and we solved that by increasing the filter aid dose. And then in addition, we were seeing some excess electron donor at this point, and this was resulted in excess production of sulfide that was oxidized to sulfur in the aeration tank. But once solving this, we were able to get down below this goal for most of the time. Or 67% of the time we were less than 0.2 NTU. You can see in these cases was each one of the filter runs, we would backwash the filter, and we would see our turbidity increasing, and then we would backwash again, and then we would increase. And so this worked generally pretty well. There's some room for improvement there, but nothing that would prevent implementation of the technology. In the next slide, we're looking at pathogens and heterotrophs. And what we saw is that we were non-detect below 2 MPN per 100 milliliters for total coliforms and E. coli, which is a requirement of the Safe Drinking Water Act and the total coliform rule. And then for heterotrophic plate counts, the goal is less than 500, and we had an average of 43 there, so we met all of those objectives. On the next slide, looking at disinfection byproduct formation, specifically the 5 haloacetic acids, which are described down here, and the total trihalomethanes. The MCLs for those are 60 micrograms per liter and 80 micrograms per liter respectively. and we clearly met those goals. We also looked at the THM formation potential, which is intended to simulate if you were to have exposure to chlorine with this water in a distribution system for a longer period of time, what would be the maximum concentrations. And for different samples, the average was 15 with a maximum of 46, which is still well under the 80. We also looked at nitrosamines, and we were non-detect on those. So the next slide, number 21. Aesthetics, one of the things we looked at was the threshold odor number. And this is assessed by a panel of people who look at a control sample of water, and then they smell this, and this is considered to be aesthetically pleasing, and they compare that to the test water, and then they determine what the threshold odor number is. The higher the number, the more smelly the water is. And the goal, the secondary MCL is 3, and our average was less than 2, or was 2.2. You can see there were a couple of cases where we had elevated TON, and this was associated with presence of sulfide in the water. So we did a number of challenge tests, as shown here on slide 22. There was one looking at the shutdown of electron donor, and then the other one was looking at shutdown of power. So in this case, we had been operating under steady state conditions, and then for 4 hours prior to time 0 here, we had operated for 4 hours without hydrogen, but we continued flow. And in this graph here, for 24 hours prior to time 0, we had been operating with flow of water, but without flow of hydrogen. So we can see the baseline concentrations of nitrate and perchlorate were 10 ppb of perchlorate and about a half of a ppm of nitrate. And then after that 4-hour period, we see our perchlorate went up to about 50 or so ppb, and our nitrate went up to about 1.5 ppm. After the 24 hours, we saw our perchlorate went up to about 140 ppb, and our nitrate went up to 8. Following, or once we reinitiated hydrogen flow, we saw a decrease in the concentrations of perchlorate and nitrate in both cases, and we anticipate that within 24 hours we would get to full recovery. The main reason for this long time taking to get down to the baseline is because these modules are in a tank that is constantly recirculated. So this is acting like a continuous stirred tank reactor, which has a high level of dispersion. And so this could be addressed by operating the reactors in batch, or possibly doing some reconfigurations of the reactor tank. On the next slide, if we take a look at the power shutdown, where we had shut down power completely, so no flow going to the reactors, no recirculation for 4 hours prior to this point, or 24 hours prior to this point, we see much less of an increase in the perchlorate and nitrate in both cases, and during the entire recovery duration, we were seeing removal of greater than 85%. So on the next slide, let's talk a little bit about this perchlorate not being able to get below 10 parts per billion. This is on slide 24. These are the snapshot of some of the optimization tests that were done. And in this case, we're looking at variations of flow rates, and then also looking at sparging of the reactor for biofilm control, either with air or before this with nitrogen. But we looked at a number of different things. We looked at feed flow rate, recycle flow rate, sparge flow rate and duration, and the hydrogen pressure. And none of these were able to get below 10 parts per billion, or 9 parts per billion of perchlorate. It's one of the questions, well, why is this? Is this possibly because the bacteria were not capable of getting down to 10 parts per billion? So on the next slide, we did some batch tests in both stages of the reactors, MBFR1 and MBFR2, and we were able to show that we were able to get below 6 ppb, in fact, to non-detect below 1 ppb of perchlorate. What we see here is our nitrate was, as soon as we went from continuous flow into batch operation, we saw our nitrate went down within about 15 minutes, down to non-detect, and our perchlorate went down to below 1 ppb in about a half an hour. and the same thing happened over in this MBFR2. But what we did see at the same time is we saw our perchlorate, or our sulfide rather, starting to increase. And with that, the sulfide started to decrease. And so this was one of the aspects that ASU looked at in detail. And so, but these data did show that the bacteria are more than capable of getting perchlorate down to 1 ppb. And so it's just a question of balancing the sulfate reduction and the perchlorate reduction. Before turning it over to Bruce, talk a little bit about the costs here on slide 26. Because we did not meet the performance objective for perchlorate, we looked at costs specifically for nitrate removal only. We looked at 6 different scenarios. These were based on different nitrate concentrations and then blending of the water. And then also we looked at results from the demonstration, and then also some additional process optimization that had been conducted by APT Water. And we compared these results to estimated costs for ion exchange and also an ESTCP fixed bed reactor that was conducted under Project 544. And then in the ion exchange comparisons, we assumed this ion exchange brine would require disposal to a sanitary sewer. So on the next slide, this shows the 6 scenarios. Scenarios 1 through 3 are based on the demonstration results. We use design data from the demonstration. And then 4 through 6, we're using optimized design parameters provided by APT Water. And you can see in scenarios 1 through 3, we had influent concentrations of 6.3, 10.2, and 18.1 milligrams per liter of nitrogen. Same things as for 4, 5, and 6. They were all at 1,000 GPM. And then we varied the ratio of bypass to MBFR treatment to get different amounts of blending, in the idea of getting effluent concentrations of 4 ppm in scenarios 1 and 4, and 6.8 ppm in scenarios 2, 3, 5, and 6. And this shows the results. This is the 30-year amortized total project costs in terms of gallons per million gallons of water treated. So this includes our capital and our operating costs. What we see in these scenarios here, 1 and 4, this is where our influent was 6.3 milligrams per liter of nitrogen, and we were targeting an effluent of 4 milligrams per liter. And we can see the MBFR was generally cost-effective and similar to the fixed bed reactor, maybe even a little bit less expensive, but pretty similar. But was definitely a lot less expensive than ion exchange. And a lot of the cost associated with ion exchange was associated with that brine disposal. If we take a look at these scenarios here, 2 and 5, where we had 10 milligrams per liter of nitrate, and then 6.8 was our goal. Again, we still see we're cost effective compared to the ion exchange. And then as we increase the concentration of nitrate, we're still cost effective, but we see this delta is decreasing as we increase the nitrate, which is to be expected. So with this, now going to turn it over to Bruce Rittman, who's going to talk about the ASU studies.
Okay, thank you. Thanks, Pat. Okay, so now, do I have control of the screen, or are you going to do that, Pat?
You have that, Bruce.
I do. Okay, let's see.
What I found is you can't click on the thumbnails at the bottom. You have to click.
Oh, I see how it works. Okay, very good. Thanks. Now I understand how to do it. Okay, so at ASU we had the wonderful opportunity to perform a bunch of special studies to really augment the understanding we gained from the field study. We did this by doing a lot of these special analyses with samples sent to us from the field, plus we did some of our own experiments in the lab and modeling. And I'll go through, I'll just highlight some of the things we did here on this work. So I'll begin with some of the work we did to supplement the understanding from the field. And so we began by doing a lot of molecular microbial ecology assessment of the biofilm communities. And here is one plot of it. And what you can see here is that we received a number of shipments over time. And if you look at the bars are the hydrogen consumption for the various reactions that are occurring. And the key thing to note here is that when you go from shipment 2 to shipment 4, there's a huge drop in the hydrogen flux. And this simply reflects the field operating strategy at that time to reduce the flow rate in order to enhance more perchlorate removal, to decrease the loading. So that was the strategy. And you can see, of course, that the loadings and the hydrogen use went down a lot. And we tracked the different types of microorganisms that happen there. And I want to call your attention to two things, and they're in red, so it's easy to see. So if you look at the dots at the top, you can see when we cut the flow rate and the total loading of all the electron acceptors, nitrate, oxygen, and sulfate, and perchlorate, there was a big increase in the number of sulfate-reducing bacteria. It was very, very dramatic increase. And also you could see down at the bottom in the bar chart that the red bars have gone up. So the red bars are the amount of hydrogen delivered for sulfate reduction. So one of the unintended consequences here of decreasing the overall loading was we induced a lot of sulfate reduction and a big increase in sulfate-reducing bacteria. So another thing we looked at is the physical and chemical characteristics of the biofilm. So APT Water has been making many improvements to the design and operation, and one of them was to enhance the physical chemical quality of the biofilm. And so we looked at that here, and I've highlighted some of the results on it. Just looking at the TSS, total suspended solids, and the VSS, volatile suspended solids. And what you can see here from this is that for the most part, well, actually not for the most part, dominatingly, the VSS was almost all of the TSS. That means the organics in the biofilm dominated. This is very significant because it means that the control strategies and the pH and also flow control strategies were extremely successful in preventing formation of any mineral precipitates, which had been a problem in times in the past. So the strategy was a huge success, and we have a very, very organic biofilm. And then we began to look at the biofilm using some very good three-dimensional microscopy techniques. And here's a very dramatic photo of it. We did staining, and this is a staining that helps us identify organisms that are metabolically active versus organisms that are basically inert or dead. And so the top graphic, the A graphic, represents for a particular biofilm sample the active microorganisms. And the bottom sample are the inert or dead ones. And you can see there's a huge difference. The biofilm is loaded with active organisms and doesn't have very many inactive organisms. So this is another really positive sign about some of the design and operating strategies that APT Water was able to implement over the past few years. Now, as I indicated before, and also Pat alluded to it, sulfate reduction was a big problem in the field study. And so we did a lot of tests in the laboratory to investigate the role of sulfate reduction and then also how to control it. So here is one of our results. This is just one result from some bench scale studies we did. And there are different across the horizontal axis are different influent concentrations of nitrate, and it goes from 1 to 25 milligrams per liter. There was the same amount of sulfate coming in all the time. And what you could see, of course, is we added nitrate, the total demand for hydrogen shown by the bars went up. That makes sense. But the really important thing to notice here is the red bars. The red bars are the sulfate flux, that is the hydrogen that was delivered to support sulfate reduction. And what you can see is as we increase the nitrate loading going from left to right, we basically squeezed out sulfate reduction. And so what we learned here was that if we could control the loading of nitrate and also oxygen as well to a certain minimum level, we could basically squeeze out sulfate reduction and eliminate the negative impacts from it. So this is one of our studies, fundamental studies, to look at that. And then we implemented this understanding by doing some two-stage studies where we used the two-stage system in the laboratory, similar to the two-stage lead-lag strategy in the field, but with one big difference. And the big difference here is that between the first stage and the second stage, we allowed oxygen to enter the water. And so we could then control the loading of nitrate plus oxygen entering into the lag MBFR. And this was not, we couldn't do that in the field. The field system was not configured to be able to do this, but we could do it in the lab. So we used this as a means to control the loading of nitrate and oxygen. And what you could see from this is that basically we could drive perchlorate down to undetectable levels without any trouble. We got complete nitrate reduction, and we had no sulfate reduction. And the arrows, the blue and the red arrows, are just pointing to the 100% removal of perchlorate and the 0% removal of sulfate. So when we implemented our strategy here to control the loadings of nitrate and oxygen, we were able to achieve essentially 100% removal of perchlorate. So there's no real problem of removing perchlorate, but you have to control sulfate reduction. Now, we did also a lot of mathematical modeling. These are mechanistic mathematical models, and I'm going to just give you a highlight. Here's a schematic of what's in one of the models. This is a model where we're looking at the perchlorate-reducing bacteria, PRB, and the denitrifying bacteria, the DB. And if you just look at the left-hand side here, you can see there are some ovals, green ovals, and those are the different kinds of organisms in there. And you see the PRB, for example, and we have heterotrophic bacteria and things in there. And so, plus all the different electron acceptors that they consume and interactions between them. So this represents it. So we use this model to try to understand what's going on inside the biofilm. And here is one example of an output that gives us some insight into what's going on inside the biofilm. And this is just with nitrate and perchlorate. So the top graphic shows you the soluble materials, things like nitrate and hydrogen and soluble microbial products. And the bottom graphic shows you the different types of microorganisms. There's a lot of things in here, but you can see that if you look at in the top graphic, if you look at the black dots, that's the hydrogen. You can see the hydrogen concentration declining from the inside of the biofilm at the membrane on the right towards the outside. And in this scenario, essentially no hydrogen escapes. It's 100% used in the biofilm. If you look at the bottom graphic, you could see that the PRB, which is shown in the red dots, there's more of them at the inside of the biofilm where the hydrogen is being delivered, and then they decline as you go out, for example. Other organisms, heterotrophic bacteria shown in purple, they have the opposite direction here. Anyway, so this gives us and you an idea of what goes on inside the biofilm, and this was a very useful tool for us to figure out about the competition or cooperation among the different organisms occurring. We also developed a model for nitrate and sulfate reduction, and of course we discovered that sulfate reduction was critically important in here, and so we developed a model for the competition. And once again, you can see in the ovals the DB for the denitrifying bacteria and the SRB for the sulfate-reducing bacteria. And so we developed this model here again, and it's the same format of the model. And I'll just show you one result here. These are from the results. These are experimental results shown in the dots for bench scale tests we did, where we varied the hydrogen pressure, and that's along the left, the horizontal axis. And you can see here on the left the nitrate, and on the right the sulfate. And what's happening, and the key thing here is as we go from left to right, we're supplying more hydrogen, and you can see that the denitrification, the nitrate removal happens earlier, and the sulfate reduction happens later. And you can see there's a zone from about around 2 or 3 atmospheres of hydrogen pressure, where you get great denitrification and you get no sulfate reduction here, because we can control the donor delivery on that. So this is again good insight to it. So we did many, many, many studies. I've only showed you a few highlights of them, but from these we came back with some very important take-home lessons of a fundamental understanding and practical application. I've just listed these critical take-home lessons here. So the first one that's really important is from modeling and our bench scale results. We showed there's no reason why we couldn't, in an MBFR, drive the perchlorate concentration basically down to 0 on this. The key of it, of course, is we had to manage sulfate reduction to minimize it. And the key to minimizing sulfate reduction was to have the proper amount of loading of nitrate and oxygen. And in the field, because of the configuration, we couldn't get a high enough loading, but in the laboratory where we could control it, we could get complete removal of perchlorate. And so the two-stage strategy that was used in the field and in the lab was really a great strategy, but the key was to have this control of the nitrate and oxygen loading to the lag MBFR. And you can see in the second bullet here, we offer some quantitative guidance as to what a good loading of nitrate and oxygen would be to the lag 1 here. And we couldn't do that in the pilot system because of the way it was set up. So with that, I think I've come to the end of the highlights of the ASU work, and I'm going to turn it back to Pat.
Okay, thank you very much, Bruce. And so as you can see from what we've presented so far is we had a field study that we were capable of meeting or exceeding a number of the different performance objectives and almost met the one with perchlorate. And with the work done at ASU, we were able to get some fundamental insights into why that is and to come up with some practical strategies on how to overcome that. And so the technology is one aspect, but we're looking at producing drinking water using a biological process. And one of the aspects of this is acceptance by the drinking water utilities, acceptance by the regulators, and acceptance by the public. And so in this aim, we did a joint project that was a survey that was funded by ESTCP and the Water Research Foundation. And so this was, looking now at slide number 42, this was to conduct a nationwide survey on biological drinking water treatment. And we weren't looking just at anoxic, we were looking at aerobic biological drinking water treatment, which is typically referred to as biological filtration. And we were looking to identify barriers to acceptance and then also identify approaches that we could increase the acceptance and use. And the response to the survey was great. We had response from 49 states. We can see in this figure here that in some states, very high responsiveness, California, 50 to 100 responses. And we also had responses from a number of different stakeholders, the Department of Defense, regulators, specifically ones who would be permitting drinking water systems, water utilities, consultants, and academicians. And the focus was mainly on the biological filtration, the aerobic, but we also looked at the anoxic as well. And so this resulted in this report shown here, which is publicly available at this website right there at the Water Research Foundation. And some of the findings that we came out is that biological treatment that's much more readily accepted by consultants and academicians than by utilities and regulators. This makes sense in 2020 hindsight. Regulators and utilities, they're looking to protect the public health, and they're going to be more hesitant about accepting new technologies, whereas consultants and academicians, they're looking more at innovation. But this highlighted the need to bridge that gap of that disconnect between these different stakeholders. We also found, in terms of doing the survey and then also looking at actual full-scale biological filters, that the actual performance of these biological filters was much better than it's perceived. We were able to remove a number of more contaminants than is thought. We're able to have safe drinking water that's produced and aesthetically pleasing water that's produced. And the perception was the opposite of that. There's also a perception that biological systems, biological drinking water systems, are difficult to operate. They're finicky. They're going to not be reliable. And the actual experience on full-scale biological filters was contrary to this perception. It actually was quite reliable. In spite of these findings, we did realize that we still need to do a better job of demonstrating or increasing acceptance, and we can do that by better education, more full-scale case studies, and better monitoring and control tools. And all of these things have been implemented to different extents since the survey was executed. So, scale up of the technology on slide 44. This has been, the path to regulatory acceptance in California has been paved, not only for this technology, but for other biological treatment systems for perchlorate, including the fixed bed and the fluidized bed reactor. A letter of conditional acceptance has been received from CDPH for the Aeronite technology, which is APT's water for treatment of nitrate using the MBFR, and full-scale tests at Cucamonga Valley Water District have been completed. And so the system is very modular, as you can see from these individual MBFR modules, so you can use it for a number of different flow rates. And one key aspect is the module design and manufacture. That know-how is critical to success, and APT Water does have that. And so the lessons learned, building upon what Bruce has talked about, we've seen over the course of this project major advances in MBFR module design and fabrication that were successful, very successful in controlling biofilm excess growth issues. And so that is now behind us. Perchlorate removal was less than 10 ppb, was much more challenging than we thought. However, with the work by ASU, we were able to identify some very practical ways to overcome this by managing nitrate and oxygen flux. And then a very exciting part of this project, I think, was use of a multidisciplinary research approach that integrated the field work and the laboratory work and modeling in order to advance the technology. So there are a number of different tools that are available. This website here on ESTCP are some webinars which look at these two projects here on biological filtration, this one 541, and then also the fixed bed bioreactor. And the technology is currently licensed and commercially available by APT Water under the name of Aeronite. As I mentioned, the conditional acceptance has been granted. And looking at application sites for full-scale nitrate removal. In addition, the MBFR is capable of removing a number of other contaminants, such as chromate, hexavalent chromium, and selenite, and Bruce Smetman is actively researching that. So, to finish, I'm proud to announce that this project has been selected by the American Academy of Environmental Engineers and Scientists for the Grand Prize in Research in its annual Excellence in Environmental Engineering and Science competition. And this was due to a joint effort of all the different aspects and because of the support of ESTCP. And with that, that concludes the formal presentation, and would be happy to answer any questions that you might have.
Thanks, Pat. At this time, we can take some questions.
This is Andy Anders, excuse me, and I'd like to say congratulations. That's a big honor, and from what I've seen of your presentation, very well deserved. Congratulations.
Thank you very much, Andy. We appreciate it very much. I appreciate your support.
Andrew, this is Marvin. Bruce, Pat, great presentation. This is very, very promising, but I do have a question. Maybe taking this to another level. Aside from drinking water, it may not be out of the realm to think that in the future we could be dealing with perchlorate in mixed plumes with other potential energetics, those energetics being very high in nitrogen, for example, RDX. What's your thoughts on possibly using this technology in a scenario where you may have high compounds, high nitrogenous levels coming from something other than just nitrite? Is this a technology, is this a wastewater treatment technology that could be used as, let's say, part of environmental restoration aside from just drinking water?
Yeah. Bruce, would you like to take that question?
Well, sure. First of all, I think in a general sense, the answer is a definite yes. And I'm not going to speak to RDX particularly because I haven't, thought about RDX. The MBFR is a platform technology that can be used in a lot of settings, including in wastewaters, industrial wastewaters, and things like this. Because as Pat said, we've looked a lot at selenate and chromate, and those are very promising. We've looked at NDMA, for example, and that's also very promising. Again, I'm not going to comment on RDX, but I think that the thing that it works really well, as long as the compounds are ones where the detoxification reaction is going to be a reduction, and then of course, if it's possible to do a microbial reduction, then the MBFR should be able to deal with it.
Okay, so you're talking, the big prize out there may also be pharmaceutical type compounds that could be in wastewater, specifically at DOD type sites. But you were saying it would have to be a reductive process in order for it to work.
Well, okay, so that's the best application. Now, you can also do them in oxidative, and we've demonstrated, an oxygen-based MBFR for situations where we wanted to oxidize things, and it works really well. You can integrate aerobic and anoxic treatments together on it. But the really great advantage of the MBFR is in the reduction mode using hydrogen, because there isn't really a good alternative.
Okay.
Yeah, and
thank you.
And
great.
And Marvin, just to expand on that, going into aerobic biological filtration, this is a very active area of research and looking at drinking water, but could be applied to non-drinking water as well, in terms of the ability of biological filters to treat not just natural organic matter or organic carbon, which can lead to production of disinfection byproducts, but to look at these personal care products and pharmaceuticals. And we're finding that generally by biological filtration in and of itself, not too successful, but quite often biological filtration is combined with a pre-oxidation step. And this may be ozone or permanganate, and we're finding in research that we're currently doing that this can be quite successful for destroying a number of different of these PPCPs.
Thanks, Pat.
Any other questions? Okay, thank you, Pat and Bruce, for taking the time to give us this webinar today. We do really appreciate it, and it is very helpful to the program to get this final summary.